A ladder AB has mass m and length 6a. The end A of the ladder is on a rough horizontal ground. The ladder rests against a fixed smooth horizontal rail at point C. The point C is at a vertical height 4a above the ground, and the vertical plane containing AB is perpendicular to the rail. Okay. We're then told that the ladder is inclined to the horizontal at an angle alpha, where sine alpha equals 4/5, and this is shown in figure 1. So this is the figure 1 they've given us as part of the question, okay? The coefficient of friction between the ladder and the ground is mu. The ladder rests in limiting equilibrium, and the ladder is modelled as a uniform rod. We've been asked, using the model, show that the magnitude of the force exerted on the ladder by the rail at C is 9 mg/25 for 3 marks. Okay, so I'm just going to begin by highlighting some key points. Okay, we have obviously the mass and the length 6a of the ladder. The end A of the ladder is on rough horizontal ground. The reason this is important is because when it's on rough horizontal ground, what it means is there is a force of friction. Okay, so this frictional force is like that. Okay. So the next part is telling us that the ladder rests against a smooth horizontal rail at the point C. So this is here, okay? And we're also told that the point C is vertical height 4a above the ground, and the vertical plane containing AB is perpendicular to the rail. So the fact that it's perpendicular to the rail means the normal force is going to be perpendicular to the plane, okay? So if we just draw a straight line, something like that, okay, and then we get our normal force like that. All right, let's actually just make that a bit neater. There we go. So the next step is the ladder is inclined to the horizontal at an angle alpha, where sine alpha equals 4/5. Okay, this is another case where the exam board isn't telling you what alpha is, but it's giving you enough information to work it out correctly. Okay. We're then told the coefficient of friction between the ladder and the ground is mu, so I'm just going to highlight what the coefficient of friction is, okay? The ladder rests in limiting equilibrium, okay? This is important because what it's telling us is the ladder isn't moving, okay? And the reason we can infer this is because friction can be in two states. Friction can either be less than the driving force, in which case there is an acceleration present from F equals ma. The other case is friction equals the driving force, and in which case there is no acceleration because there is no net resultant force. Now bear in mind, no acceleration doesn't mean stationary, it just means its speed isn't changing. So it can be moving at a constant speed, and that can be 0 as well, okay? And then we're also going to highlight that the ladder is modelled as a rod, okay, as a uniform rod. And the reason uniform rod is important is because it tells us that the centre of mass is halfway, okay? And what this just means is that if we look at our rod, the point where our mass acts, or our centre of mass, is going to be halfway between A and B, or A and B, like that, okay? And the final thing I'm going to highlight is that we need to find the force exerted on the rail at C, and I'm going to highlight the final form. I'm just going to make 2 more annotations on our diagram. I'm going to annotate first the reaction force. Okay, so it's like this. Just going to add that F equals mu times the reaction force. And I'm also going to draw on our weight component, okay? And this is 3a. So 3a is between our center of mass and our point A, like that, okay? The next thing we're going to do, okay, so as part of solving this question, is you should always resolve your forces in the same direction, okay? So what I'm going to do is I'm going to resolve this in the perpendicular to the plane. So this is going to be mg cosine alpha, like that. Now, what we need to do when it says show that the magnitude of the force exerted on the ladder, okay, like this, what this is actually asking us to do is it's asking us to find n, okay, because the force exerted on the ladder by rail C is here, and that is our normal contact force, okay? So from here, what we're going to do is we need to look for a way to find n. And the best way I can think of to do this is to take moments about A, okay? And I'll explain what this means. So when you take a moment, or take moments about A, you are looking at all the forces which can rotate the rod about the point A. So point A becomes the pivot, all right? So if you look at mg cosine alpha, it's going to try and push the uniform rod or the ladder in this direction, okay? So in a clockwise direction, but the normal force is pushing it in a counterclockwise direction, okay? And because the rod is in equilibrium, okay, and it's not moving in either direction, what we can say is that the anti-clockwise moment and the clockwise moment, so remember the moment is just a turning effect, okay? So the anti-clockwise and the clockwise moment are the same, okay? So now we know we need to deal with moments. What we just need to do first is write out our formula for a moment, okay? So what I'm going to say is a moment is a force times the distance to the pivot, all right? And in this case, the pivot for us is A, all right? So what I'm going to do now is I'm going to say that the anti-clockwise moment equals, so just fix that in, sorry, equals our clockwise moment, like that, okay? So now we need to find out anti-clockwise moment. So we know that the anti-clockwise one is n, because that's what's pushing it this way, and this direction is anti-clockwise. So the force is n, so we say n times, now we need a distance. To find the distance, effectively we are looking for AC, okay? So we are looking for A to C, this distance here. Okay, so what I'm going to do is I'm just going to draw a new diagram just a bit lower down, and I'm just going to use this to find all the distances we need for this part of the question, right? So to begin with, we know that the height is 4a, and we know that the opposing angle is alpha, which makes this side the opposite, this side the adjacent, and this side the hypotenuse, okay? We also know that sine alpha equals 4 over 5. So from here, we have two methods we can use to find what the height, the length AC is. So I'm just going to actually mark on here that this is A and this is C, okay? The first way we could do it is we could use trigonometry to find what the hypotenuse is, and then reverse the Pythagoras theorem to get 3A, or to get the adjacent, and then we can see that. Our other option, which is the one the exam board has gone for, is to leave everything in terms of sine alpha. So what we would do is we would use the fact that sine alpha equals the opposite over the hypotenuse, and then because we're looking for the hypotenuse, we would say the hypotenuse equals the opposite over sine alpha, all right? In which case the opposite for us is 4a, so we say this is n times 4a over sine alpha, and this equals, now because we've got our distance AC, that's done. Now let's find the clockwise moment, and the clockwise moment is very simple. It's just mg cosine alpha, so that's our force, and that's the weight of the ladder, so mg cosine alpha, and then our distance is going to be the distance from A to the midpoint, which is 3a, sorry, so times 3a, like that. Okay, from here what I'm going to do is I'm going to cancel A from both sides like that, and what I'm going to do is I am going to divide both sides by 4 sine alpha. Okay, so we're going to get that n equals mg cosine alpha, and then it's going to be times 3 over 4 and then sine alpha, because remember we're dividing by 4 sine alpha, which means we're multiplying both sides by sine alpha over 4. Okay, from here what we're going to do is we're going to use the fact that sine alpha equals 4 over 5 to get that cosine alpha equals 3 over 5. And the way you would get this is by doing what I said initially. So knowing that because the sine alpha is the opposite over the hypotenuse, this means the ratio of the opposite to the hypotenuse is 4 to 5. So the hypotenuse in this case would be 5a, and then using the reverse of the Pythagoras theorem, you would get the adjacent as being 3a. And since cosine alpha is the adjacent over the hypotenuse, that would be 3a over 5a, which is just 3 over 5. Okay, so this means that we get mg times, so cosine alpha is 3 over 5. This 3 over 4 is carried straight down, and then times sine alpha. Well, sine alpha was 4 over 5. From here, what I'm going to do is just cancel the 4's, and then we're going to say that n, so n equals, there we go, so we've got 3 times 3, so that's 9. So these two 3's become 9, and this 5 and this 5 becomes 25. So this is going to be 9 over 25 g, and then in brackets as required. Okay, like that. So this question is worth 3 marks. Your first mark comes from stating you'll be taking moments about point A. Your second mark comes from knowing that the anticlockwise moment is the same as a clockwise moment to get that n times 4a sine alpha equals mg cosine alpha times 3a. And then your third mark comes from working out that cosine alpha is 3 over 5 and that and then getting that n equals 9mg over 25 as required, like that. Part B has asked us hence or otherwise find the value of mu, okay? And this part is worth 7 marks. So the first thing we're going to do is we actually need to split our normal reaction force at this point here, point C, into horizontal and vertical components like I've drawn on the diagram, okay? But what I'm going to do first is I'm going to draw a vector triangle just to show how this can be done. So we're going to begin with a vertical somewhere down here. Okay, we then will have a horizontal along like this, and we will draw in our normal reaction force as we see it, something like that. Okay, just going to put the arrows on to show that they are vectors. This is a normal vertical force, and this is our normal horizontal force. Let me just make that a bit bigger. Normal horizontal like that. So to resolve these forces, what we can do is we can move this normal vertical to the other side, sort of like that, okay? Because at the end of the day, it's a vector, so the fact that it is showing where this purple arrow is going, so it's going first horizontally, then vertically, it means we're allowed to do that, okay? So we have vertical on this side and horizontal on the base like that. So then the next step is to add our angle, okay? As you can see, we have an angle of alpha here, okay? And this is between our base and our slope here, okay? So if this angle is alpha and this base here is parallel to our normal horizontal here, what this means is, this means also that this angle here is alpha. Okay, so if this angle here is alpha, so it would be sort of an imaginary thing here, you'd have a horizontal here, so I'm just going to draw that in purple, just as a dotted line, something like that. This is our slope here. We know that this is alpha, and we know that this is perpendicular to this, okay, because the fact it's a normal force means it's perpendicular to our slope. So this means that this whole component here is 90 degrees. So this internal bit is 90 minus alpha. So we can say that this is 90 minus alpha, and that makes this part alpha because all the angles need to sum to 180. We know this is 90, so that means that this bit is alpha, okay? So now that we understand that the angle between the normal reaction force and the vertical is alpha, as we have here, we can start to resolve it. Okay, so I'm just going to rub out some of the additional markings that we don't really need for this question, something like that. Okay, I'm going to just make this alpha here. So what you can see, if this is our angle of interest, alpha, this means the normal horizontal here is opposited. So what we can do is we can add the opposite symbol there. If that's the opposite, this means NV is the adjacent, and we know that the normal reaction force N, let me just label it on, N, is our hypotenuse. Okay. So now that we understand how to split our normal reaction force into its horizontal and vertical components, we can start by resolving our forces, okay? So to begin with, I'm going to say resolving horizontally, okay? Doesn't matter which one you start with, you can do horizontal or vertical first. I'm just going with horizontal because that's the way the marksman has done it. So what you need to do if you want to resolve horizontally is you need to make sure all the forces acting to the right balance or equal all the forces acting to the left. So the only force we have acting to the right is our frictional force, okay, which is mu r. So what we can say is our frictional force F equals, now our force acting to the left or acting in the opposite direction to the friction is NH, okay, which is our horizontal component of our normal, okay. So I'm just going to say this equals NH. From here, okay, what we will have is that our frictional force F equals, so to get NH, we will come back to this triangle we have here, NH, so this is the opposite side to our angle, so this means we will be using sine, okay, because remember from SOHCAHTOA, you have SO, which is SOH, okay. So the normal component of our horizontal force is going to be N sine alpha. We already know that N is 9 mg over 25, so what we can say is that therefore our frictional force must be equal to 9 mg over 25 sine alpha, like that. Next, let's resolve vertically. Okay, so we can say resolving vertically, like this. Okay, again, when you want to resolve vertically, you need to make sure the sum of all the forces going up equals the sum of all the forces coming down, okay? And that is because we know that the ladder is in equilibrium. So, the forces going up, we have R, which is our normal reaction to the ground. So what we can say is that R plus the other force we have going up is our our vertical component of our normal reaction force. So R plus NV equals. Now, the only force we have going downwards or acting down is our weight component, which is mg, like this, okay? All we need to do now is replace for NV, and then we can move to the next step. So NV is the adjacent side to our angle, okay? And what that means is NV will be our hypotenuse times the cosine of alpha, okay? So what we can say is that here we have R plus N cosine alpha equals mg. And N, as we know already, is 9 mg over 25. So this means that R plus 9 mg over 25 cosine alpha equals mg. Like that. Excellent. We now have our horizontal and our vertical components of our forces resolved. What we can now do is we can use our equation for the friction in terms of a force and its normal reaction, which is F equals mu R, to eliminate F and R, replace it with mu, and we can solve from that, okay? So what I'm going to say now is using F equals mu R, like that. What we can say is that 9 mg over 25 sine alpha equals mu times. Now to find R, what we need to do is we subtract 9 mg cosine alpha over 25 from both sides. So this will equal mg minus 9 mg over 25 cosine alpha, which is something like that, okay? So what you would notice here is that each term has an mg in it. So what you can do is you can cancel this mg, which will leave us with 9 sine alpha over 25 equals mu times 1 minus 9 cosine alpha over 25, like that, okay? From here, we can replace sine alpha and cosine alpha as we worked these out in the part before, and we will say that sine alpha equals 4 over 5 and cosine alpha
equals 3 over 5. So what we'll end up with is 9 over 25 times 4 over 5 equals mu 1 minus 9 over 25 times 3 over 5, like that. What we can then do is we can rearrange for mu. So mu would be 9 over 25 times 4 over 5, all divided by 1 minus 9 over 25 times 3 over 5. Okay, like this. And if you put this into your calculator, what you would get is an answer of 18 over 49. So this part is worth 7 marks. Your first mark comes from claiming you're going to resolve horizontally. Your second mark comes from correctly getting that f is 9 mg over 25 times sine alpha. Your third mark comes from stating you're resolving vertically. Your fourth mark comes from getting that r plus 9 mg over 25 cosine alpha equals mg. Your fifth mark comes from showing somewhere that you've attempted to use that force, the frictional force, is the coefficient of friction times your reaction force. Your sixth mark comes from eliminating your reaction force and friction and solving for mu. So what we have done that from here, and we have shown some attempt to solve for mu, which is what we have down here. And your seventh and final mark comes from getting that mu is 18 over 49.